Oops, let me just go that, yeah. Yeah. So here we see these dark clouds, and if I now, this is down the Carina Nebula. This is a beautiful image from the Hubble Space Telescope. So this is in the light that we see with our own eyes. You see here these very dark regions, and if I would point my telescope, one of my telescopes, at these dark regions, that's where I would find a lot of molecules, and that's where I would also see new stars and planets being formed. And as I mentioned, these clouds are so dark because they contain these tiny little dust grains that you can think of as silicates or carbonaceous material. They are very small, only a fraction, a thousandth of a millimeter, a tenth of a micrometer, and they make up by mass about 1% of these clouds. So these clouds, one of these dark clouds that you see over here, is mostly hydrogen, molecular hydrogen, temperature very low, just above absolute zero, densities about 10,000 particles per cubic centimeter, which is much more empty than the best ultra-high vacuum that you have in a laboratory on Earth. It's mostly neutral. The ionization fraction is very low, maintained by cosmic rays, which penetrate into the cloud. Collision times are long, so we are not thinking of things that happen on a minute time scale, but we are thinking about collisions that happen maybe only once a month, and the time scale to reach chemical equilibrium may be of the order of 100,000 to 1 million years. So, for me, as originally also a chemist, for me this is really a unique physical and chemical laboratory in order to study chemical processes in an environment that's different from what we have here on Earth. So let's look at an example from elements to molecules. Water, of course, 2 hydrogen and oxygen. How simple can it be? Well, it turns out actually that the only way to make water is actually on the surfaces of these tiny little dust grains that you see over here. And this has been simulated, measured actually in laboratory experiments in various places, in Leiden, Paris, and in Japan. There's a hydrogen atom landing once a day on the surface of a grain. It finds maybe another hydrogen, goes off as H2. But it can also find an oxygen. Yeah, there it finds an oxygen. 2 oxygens finding each other, making molecular oxygen. And then they make hydrogen peroxide, and then actually, yeah, there they make 2 water molecules. And so this is happening on the time scale maybe of a day, and now we fast forward to say 10,000, 100,000 years, and we make lots and lots more molecules of water, and then we make sort of this icy layer on the surface of the grains. And in fact, the bulk of the water that we have here on Earth, that is in your body, that is in the sea here around St. Petersburg, that water, the bonds between those water molecules were already formed 4.5 billion years ago in the cloud out of which our solar system collapsed. So think about that the next time you drink some water, that those water molecules are already 4.5 billion years ago. Of course, they have evaporated and recondensed again, but the initial bond was formed on these tiny dust grains that you see there. So as one of my colleagues put it, the water on Earth is actually older than the sun itself. Good. Well, we find not just water, we find lots of other molecules, surprisingly, under these conditions. If you look at the more diffuse clouds, we see carbon monoxide, we see H3 plus there, simple molecules, but also already quite complex. Polycyclic aromatic hydrocarbons that we see there. If you go to the denser clouds, then the molecules are shielded from UV radiation, and we start to produce more complex species, like dimethyl ether that you see here, also these very long carbon chains. If you go to the accretion disks around young stars, then which planets are made, we're starting to probe the chemistry there. And then in comets, as we will see, is actually a very rich chemistry there. We see lots of molecules there that may or may not end up on a new planetary system. Of course, stars don't have eternal life. They will run out of material for nuclear fusion. When they do so, they will swell up, and they will actually return a lot of the elements that they created through nuclear fusion back into the interstellar medium. And that's when a whole new cycle of star and planet formation can occur again, now enriched with new elements that were formed there. We see also some interesting molecules, and that's under those conditions, such as, for example, fullerenes, the buckyballs. So we find specific molecules under specific conditions, which is nice also to have a diagnostic, not just of chemistry, but also a probe of the physics that is going on. Now, one of the big new astrochemistry machines that we have is actually the Atacama Large Millimeter Array. That is particularly well suited for observing molecules because we can look there at the pure rotational transitions of the molecule as they tumble end over end in interstellar space. And that is the first worldwide collaboration in astronomy between Europe, East Asia, and North America to put this large array actually on a high altitude plane in northern Chile. And just to give you an impression, in just 30 seconds of integration time, if you point at a high mass star forming region, you find all of these lines, all of these fingerprints of the molecules that we can uniquely identify with dimethyl ether, sulfur dioxide, acyl cyanide, etc., etc. And so basically each molecule has its unique barcode with which we can identify it in space. What have we discovered so far? Well, lots of simple molecules, lots of complex molecules. I showed you already some of them. Here we see a few other ones, such as this simple sugar, although not yet sugar in the chemical sense. Ethanol, there's actually quite a bit of alcohol in space. Probably the Orion Nebula has enough to fill 10 to the 27 bottles of whiskey, in case, or vodka, in case you're interested in that. But some of the prebiotic molecules, like the simplest amino acids, bases like purine and pyrimidine, they have not yet been found. And also this molecule that you see over here, which may not be necessary for the origin of life, but is certainly important for the maintenance of life, as we just sampled it, is not yet been detected. But what it shows is actually that these molecules are not that much more complex than the ones that we've seen already. So with ALMA, we can dig much deeper into searching for these complex molecules. Here you see some recent detections, tricarbon molecules such as isopropyl cyanide, and also the first chiral molecule here, propylene oxide, that has sort of a mirror symmetry here that you can see that has also been detected, although we cannot yet determine whether one of the two forms is enhanced or not. The large carbonaceous molecules that I mentioned already, especially the fullerenes, have been seen, and also very recently benzonitrile is sort of the first aromatic molecule that has been uniquely identified. The PAHs, we know that they are there as a class of molecules, but we cannot say whether it's coronine or one of the other PAHs that we are actually observing.